Welcome to the next session on Advanced ANSYS Workbench tutorials. In this session, we will analyze a swing check valve for its modal analysis. We will start by double-clicking on the modal module. We'll first go to engineering data and double-click. Engineering data sources, general materials. I'll be using stainless steel as the material for analysis, so I'll bookmark it. Also, I'll use one more material, which is CPVC. I'll give the properties. The first property is density, 1650 kg per meter cube. Next, I'll click on isotropic elasticity, double click. Young's modulus value is 3.1 gigapascal, so 3.1 E9. Value of Poisson's ratio is 0.386. Also, I'll apply one more material, which is for the gasket. That will be EPDM rubber. For which we'll give the value of density 1100 kg per meter cube. We'll give the value of isotropic elasticity. Young's modulus is 4 megapascal, so it is 4E6. Value of Poisson's ratio is 0.5, but the moment you give 0.5 here, bulk modulus becomes infinity, and here you can again see a question mark, which means this is not an acceptable value, so I'll just make this as 0.485. Such that we get some value of bulk modulus, and you can see this question mark over here has disappeared, which means you have successfully given material properties to rubber. I'll go to project, update project. Next, I'll go to geometry and right click. Since I have the model made with me, I'll directly import the model. Then I'll go to model and double click. First, we'll go to geometry. I'll remove the cap assembly, so I'll just hide it. You can see here this is a swing assembly. This one is also part of it, and this is the part of it. This entire part is the swing assembly. And here again you can see this is a part of the swing assembly itself. So we'll keep it, and this is the gasket which you can see. Now if you want, you can keep the cap assembly. So I'll first show you by keeping the cap assembly as it is. So I'll unhide it, show body. I wanted to show you the inner part as well. So now that we have seen the cap assembly and the swing mechanism and everything, so we can just go and see you can see this is a check valve body. This is the body, this is the cap, and this is the swing assembly which you can see inside, and this was the gasket. So now I'll go to geometry. Now you will select all of these and you'll give the material as, say, stainless steel. Gasket part, I will change it to EPDM rubber. So let's keep all of them at the start. I'll go to mesh and generate mesh. You can change the sizing as per your requirement. I'll leave it to the default size itself. Now once this is done, I'll go to modal. I'll right click here, insert, fix support. This end I'm going to fix. Again I'll right click and insert, fix support at this end as well, and apply. Then I'll go to solution, right click, solve. So once we get this, here I'll right click, select all, right click, create more shape results. I'll go to solution and solve once again for all the 6 deformations. Now we have 6 deformations because if you check in analysis settings, by default, max modes to find are 6. So let's see the first deformation. Now I will show you first by keeping the cap assembly, and then I'll remove the cap assembly and I'll show you once again what happens. So you can see this, I'll animate, you can see this part, the ring over here for the cap assembly which is moving. Here the frequency is 0 Hertz and the deformation is 5.9367 meters, which is quite a high value. Then we'll go for the second one. You can animate this and see again the frequency is 0 Hertz, which means these are just no frequency, and yet you can see a deformation of 4.256 meter. Next we will see for the third deformation for frequency, that is 2.353 to 10 raised to minus 4 Hertz, which is actually a very small value. The deformation is 5.817 meter. You can see the pattern of motion of this ring. Then we will see the total deformation 4 for frequency of 4.67 into 10 raised to minus 3 Hertz. Maximum value of deformation is 6.1161. That too over here. So you can animate and check this. For the fifth one, the frequency is 5.77 into 10 raised to minus 3 Hertz. Deformation is 4.86 meters. You can check this animation as well, the pattern of its motion. And then we'll go for the sixth deformation. The frequency is 7.4 into 10 raised to minus 3 Hertz and the deformation is 6.48 meters. You can see the pattern of the motion of this top ring of the cap. Now once this is done, I will go to geometry and now I'm going to remove this cap assembly over here. Right click and hide body. So basically nothing required a change. Just observe the pattern of deformation now. You can see there is a deformation here. And this internal portion also you can see the pattern of its motion. The deformation is 4.256 meter for 0 Hertz. Now I'm seeing the second deformation. We'll go for the first one as well. You can see the pattern of its motion. You can see how this body is vibrating under this frequency, which is 0. Then you have the third one, which is important. And you can also see this pattern. Then we have the fourth one. You can see the internal portion also vibrating. You can see the outer portion. And then fifth one. You can see the motion is quite visible here. And the internal one also you can see. Then we'll go for the sixth one, which is the last one we have selected. You can increase the number of max modes to find to more than 6 as well. I will leave it to the default value 6. So once you have seen all of these, what I'll do is I will again go to geometry and remove the swing assembly as well. So I'll just hide this. Also there is this part here. I'll remove this. I'll just hide it for some time. So what remains is only this body and the gasket. Now I want you to see the deformation of this body. This is for the first one. This is for the second one. Then we have the third one. This is only the check valve body and the gasket involved. You can see the pattern of motion of the gasket because it is weaker rubber, so you can see what is happening to it. Then you have the fourth one. This is the fifth one. And this is the sixth one. Now we can only solve for this swing check valve. So we will just change the material to CPVC. So I'll select the check valve body. I'll change this to CPVC. I'll leave the gasket as it is. I'll go to solution and solve once again. So once this is done, we'll go for the total deformation 1. You can see here it's 0 frequency and 6.25 meter deformation. Then we'll go for the second one. Again 0 hertz, 4.75 meters the deformation. Then we'll go for the third one, 5.96 meter deformation for a frequency of 0 hertz. You can see this is the third natural frequency of the body. The fourth one is showing a deformation of this sort, 5.7 meter deformation, and the frequency is 2.7 to 10 raised to -3 hertz. Then we have a frequency of 4.83 into 10 raised to -3 hertz and deformation of 5.426 meter. And this is the last one. Now since I've changed the material, you can see a change in these values. What I'll do is I'll go to geometry once again, check valve body. I'll change this material to stainless steel and solve once again. So now you can just see the difference in the value and the pattern of motion. When you used CPVC, the motion was more visible in the case of CPVC as compared to stainless steel, because stainless steel is a metal and CPVC is a plastic, so you can see the difference in the swing check valve pattern of motion and the frequency and the deformation. Steel will show better results as compared to CPVC. So again, you can run this and you can check. You will see there is a vast difference in the pattern of motion. So with this, I end the session. I hope you have understood the modal analysis of swing check valve. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.